Hello everyone, this is Ashok, your personal guide and mentor. I welcome everyone to my YouTube channel AKB Tutorials. Here we are going to discuss and cover some important concepts of mechanical engineering that are very useful and helpful for competitive exam and job interviews. So let us start today's session. Hello friends. So today we will see one of the important topics. So that is deformation of paper bar. So we have already seen the deformation of a bar, but today we will see the deformation produced in a paper bar. Say a circular paper the diameter increases from small d to capital D, and the length of the bar is given as L. Now, how to find the deformation of this bar? And this bar is under load. Say tensile load is acting over the bar is P. P is the load acting over the bar, that is a tensile load, and the diameter of bar increases from small d to capital D. So that means at every point, what is taper? So we should know taper. What is taper? A gradually increasing or decreasing bar is known as a taper or taper bar. Now, this is a circular taper. What it means by this circular taper? So, this side view, if we see, this is a circle of diameter small d. Small d is the diameter of this circle, and this side, if we see, this is a circle of diameter capital D. Now the bar is varying its diameter from small d to capital D and under load P. The length of the bar is L. Now consider a small elemental area of dx thickness at a distance x from the left end or smaller end. So we have considered an element of dx thickness or dx length. So if we consider another element here or here, so what is seen is the diameter of all the sections are different. Now in this condition we have to find the deformation produced in the bar. So how many elements are there? There may be thousands of elements or infinite number of elements. So all the elements are under same load P acting over that element. Now we have considered that element, so we are drawing separately that element. Elemental length is dx, and say the diameter is, we don't know the diameter say here it is d of x. Okay, now we will find what is d of x. So d of x is given by, so this diameter, that is small d plus some increment. What is the increment in diameter? So if we see here, so this much and this much is the increment at distance x from the left end. So what is the total increment from this end to this end? That is capital D minus small d, the total increment over a length L. So per unit length, what is the increment? D minus d by L, and for length x, it will be given by d plus capital D minus small d by L into x. So we have got the diameter of the element and length of the element. Now, what is the area of this cross section of this element? That is, say, denoted by x, is given by pi by 4 into d square. That is, what is d value? D plus capital D minus small d by L into x whole square. So we can write pi by 4 into d plus some constant into x whole square, because this value is a constant value for a given taper. This taper is given to you where small d and capital D are the diameter of the taper and length of the bar, taper bar is L. So d minus d by L is a constant. So we have taken as K. Okay. So for this element, say this element will deform by some amount. Okay. So we are denoting by d dx is the deformation produced in the bar. So we can write d dx is equal to, given by the formula P into L by A into E. So we can write P, the load acting over the element, P, this element is also under load, P. So P into L, what is L? Here L is d of dx, and area is given by this, that is this one. We will write Ax, and say Young modulus of material of the bar is given as E. So this is the deformation produced in this elemental bar. Now, what is the total elongation produced? So if we consider all the elements separately and find the deformation produced in all the elements and add, so it will give the total deformation produced in the bar. So total deformation is given by total deformation. It is given by integration 0 to L this term, that is P into dx divided by what is area? Ax, that is pi by 4 d plus kx whole square into E. Okay, so if we do the integration of this, so it will give 4 PL by pi E into small d into capital D. So this is the deformation produced in the bar under load P, where the taper bar one end diameter is small d and the another end diameter is capital D, and the length of the bar is given as L. So this will be the total deformation produced in the bar. So this is the case of a taper bar of circular cross section. Now we will see the another taper bar, that is taper bar of rectangular cross section. Say a taper bar of rectangular cross section. So if we see, say this is the taper bar of rectangular cross section which have constant thickness. This is the taper bar which is having thickness, say it is T throughout, and this is the thickness T throughout. It is T the thickness, L is the length of the bar, and at one end, say it is small b is the width at one end, and at the other end it is capital B. So this is the rectangular taper bar is given, and we have to find what is the deformation produced in this taper bar. Taper bar is under load P. Now consider an element of thickness dx at a distance x from the left end. So dx is the thickness of this taper bar at a distance x from the left end. Now if we draw this element, so what is the elemental length is dx. The force acting on the element is P, because all the elements under same load P, and say the area of cross section of the element is AX. Now we find the width of the element, because the width at the left end is given by small b, and width of this bar at the right end is given by capital B. So what is the width at a distance x from the left end? Say it is given by bx. Bx will be always greater than b, so we can write b plus some increment. What is that some increment? Total increment while moving from left end to right end is given by capital B minus small b divided by L. What is this term? This will give you the increment per unit length of this taper bar, and for x length you can write small b plus capital B minus small b by L into x. Okay, it can be written as b plus k into x. K is some constant. Okay, so now we have got bx. So area of the element is given by ax is equal to bx into the thickness. Thickness T is the thickness throughout is same. So now we have got area, we have got the length of the element, we have got this load acting on the element. So the elemental deformation, so it is given by, so d of, say d of x. Okay, and d of b of, okay, elemental deformation Okay, it is elemental deformation. It is given by P into L by A into E. Okay, so have P is the load acting on this element P. What is the length of the element? It is given as dx. What is the area of the element? It is given by bx into t, and E is the Young's modulus of elasticity. So that will be the deformation produced in this element whose length is dx. Now, if we find the total deformation produced in the paper bar, that is total deformation, it is given by the integration of 0 to L, integration of this value, that is P into dx by bx into t into E. So we can write integration 0 to L P into dx by bx. Bx is equal to b plus ax into t into E. So if we do the integration of this expression and put the value of k in the expression, so it will give p by k into t into E log capital B by small b. Okay, this will be the result. So p by kt E natural log capital B by small b. So we have seen the deformation produced in a circular taper bar, also in a rectangular taper bar. Now we'll see some problems related to this taper bar. Now the first problem, so I am writing the first problem. A flat steel plate, a flat steel plate of trapezoidal section has a thickness of 20 millimeter and tapers uniformly from a width of 30 millimeter 80 millimeter to 30 millimeter, 80 mm to 30 mm in a length of 500 millimeter. What will be the elongation of the plate under a axial load of what will be the elongation of the plate under an axial load of 200 kilonewton take E is equal to Young's modulus of elasticity of the material is given as 205 gigapascal. So a flat steel plate of trapezoidal section. So we have seen the derivation. Now we'll see. We'll try to draw this. So this is the taper bar. So one end, the width is 80 millimeter and the other end is 30 millimeter. And the length of the bar is given as 500 millimeter. And the uniform thickness of this bar is given as uniform thickness is 20 millimeter. So this thickness is 20 mm. So directly we can put the formula. Okay, where K? So we have got K is equal to capital B minus small b by L. So in the formula. So that means 80 minus 30 divided by L is equal to 500. So it is giving 0.1. The K value, that is the constant. Now the elongation of the bar, the total elongation of the bar is given by the formula P by K T E into log capital B by small b. Okay. So here P is given as 200 kilonewton. So we can write 200 into 10 to the power 3 Newton. Divided by K value, we have got 0.1 into the thickness is given by, directly we can write 20 millimeter. So 20 KTE is given as 205 gigapascal. So in pascal it is 10 to the power 9 Newton per meter square into log capital B value is 80 divided by small b value is 30, and if we solve this by using calculator, so it will give you 0.488 millimeter. So this is the answer of this question. So if we know the derivation, it is very easy to solve the problem. Now we'll see one more question. That is question number 2. So we'll see another question related to this taper bar. That is question number 2. A tapering bar of 1 meter length has diameters of 20 millimeter and 50 millimeter. At the two ends. Find the elongation of the bar under an axial tensile load of of 250 kilonewton. 250 kilonewton. Take E is equal to 200 gigapascal. So a taper bar of 1 meter length. So now draw this taper bar. This is a circular taper. So length is given as 1 meter. So the data are 20 millimeter and 50 millimeter. So this side, this end diameter is 20 millimeter and the other end diameter is 50 millimeter. Okay, the length is 1 meter, or we can write is 1000 millimeter. Okay, the bar is under a load of 250 kilonewton. 250 kilonewton. So 250 kilonewton. So the bar is under 250 kilonewton. One end diameter is 20 millimeter. Other end diameter is 50 millimeter. So D is equal to small d is equal to, that is 20 millimeter. Capital D is equal to 50 millimeter. L is equal to 1000 millimeter. P is equal to 250 into 10 to the power 3 Newton per meter square or Pascal, and E value is given as 200 gigapascal into 10 to the power 9 Newton per meter square. Now we have to find the deformation of the bar. So we have seen the derivation. So delta L is the total deformation of the bar. Total deformation of the bar is given by 4PL by pi E into small d into capital D. So this is the total deformation produced in the bar, and it is given by 4 into, just we are putting the value, that is 4 into, what is P value? 250 into 10 to the power 3 into L value is 1000 millimeter into 1000 divided by pi into E value is equal to 200 into 10 to the power 9 into small d is given by, what is small d? 20 millimeter into capital D is equal to 50 millimeter. So if we solve this, so we will get 1.55 millimeter. So friends, this is all about the taper bar, and I hope this will clear your ideas regarding this deformation of taper bar. It is not hard. It is same as that of the deformation of a plain bar, that is dl is equal to p into l by a into e. Same formula, but as the area at every point is different, so deformation produced in every point will be different, and if we add all the deformation, that will give the total deformation produced in the bar under this load P. Okay, thank you all about this video, and we will meet you soon in the next video. That's all for today's session. We would continue further on this topic in the next session.
Keep being connected with us and ask any question in the comment section. Like, share, subscribe, and don't forget to press the bell icon to get notified for future videos. Thank you and see you soon.